This video is going to be doing a quick overview of specific heat and going through some example calculations involving specific heat for the Chem 099 course at St. Charles Community College. So, specific heat is a physical property that every substance has that measures the amount of energy it takes to take 1 gram of that substance and raise its temperature by 1 degree Celsius. So specific heat is in some ways similar to something like density. Every substance has its own density value, which is the relationship of its mass to its volume. So specific heat, every substance has its own specific heat. But what it's looking at is how much energy it takes to change the temperature. And the specific heat value is based on both the amount of substance you have and how much energy it takes to move that. So water is one of the specific heats you will probably use the most often when you're doing these calculations. So water specific heat is 4.184 joules per gram times degrees Celsius. I know the weirds are funky, or the units are funky. It involves both energy, which is joules, mass, which is grams, and temperature, which is degrees Celsius. That's why specific heat has all of those. So water's specific heat value is listed there, but that's for when water's liquid. When it's ice, it has a different value. When it's steam, so when it's a gas, it has a different value. So substances have different values for their specific heat, depending on their state of matter and then what substance they are. So again, every substance has its own value. So just as an example, if I had 1 kilogram of water and 1 kilogram of iron, and I added 4,184 joules of heat, a number that I picked, whatever, but I added the same amount of heat. So like I put them on the stove, okay, and I turned up the burner, and I added exactly 4,184 joules of heat. The temperature of water would have only went up 1 degree Celsius, but the temperature of iron would have went up 9.3 degrees Celsius. So I added the same amount of energy to it, but the temperatures varied on how much they moved. That's the measure of specific heat. So water's specific heat is different than iron's specific heat. So in this scenario, water's specific heat is bigger. It takes more energy to move this mass of water's temperature, which honestly for water, it's a really good thing for us. We're mostly water. And human beings, we have to be within a specific temperature range to stay alive. So, but we're exposed to all kinds of, humans can be exposed to all kinds of climates on our planet, right? There's the really cold stuff, there's the really hot stuff, and then there's the stuff in between. So water having a really high specific heat value, it means we can be exposed to a decent amount of energy, like heat, like from the sun, or lack of energy, and the temperature inside of our bodies doesn't change very much. And obviously you can be exposed to too much heat or a lack of heat to where the temperature does change, and then our temperature gets outside of the range that is allowed for us to be alive, and that's when people can die from like heat stroke and from like hypothermia. Okay, so water having a high specific heat is good. And another example of that is, our oceans are made of water. The sun is shining on the oceans a lot of hours during the day, which means it's transferring energy to the water in the ocean. Well, it's important for our planet that the waters stay liquid and don't boil off. So water having a high specific heat helps make that happen. So something with a high specific heat takes a lot of energy to raise or lower the temperature. Something with a low specific heat, it doesn't take as much energy to raise or lower the temperature. So this is just an example of some different specific heat values. You would never be expected to memorize these numbers. They would be given to you unless it's the thing that you're solving for, but we can see that they vary. But water, right here, is by far the biggest one on our list. And it looks like it gets down to lead. Nope, looks like gold wins. So what that means is it doesn't take a lot of energy to raise the temperature or lower the temperature of gold. So an example of this, again, like aluminum foil. So aluminum's right here. If you use aluminum foil when you're putting something in the oven, like to cover it, when you take it out of the oven, that aluminum foil will cool off faster than the container that it's in. So let's say it was in like a glass dish. That's a bad example. But still, the aluminum foil cools off a lot faster. Water, once you've boiled water, it stays hot for a pretty long time because it takes a lot of energy change for the temperature to decrease. Okay, so specific heats are just constants. They're just a number. Every substance has one. The bigger the number is, the harder it is to heat it up, or the harder it is to cool it down. It works both directions. The smaller the number, the easier it is to heat it up or cool down. Okay, so the specific heat had those funky units, right? The joules, the grams, and the degrees Celsius. So this equation is how we can use that specific heat value to do some math to predict either how much heat it would take to take a sample of something and heat it up to a certain temperature, or we can solve for any of these variables. Okay, so heat, its variable is the letter Q, and its unit in this equation is going to be joules. Mass is abbreviated by the lowercase letter m, and its unit in this equation is going to be G. Specific heat, that's these constants that I just showed you the table of. Its variable is the lowercase letter s, and its units are going to be joules divided by grams times degrees Celsius. And temperature change, its symbol is going to be delta T, which stands for we're subtracting two temperatures. Okay. And its units are going to be degrees Celsius. So it's going to be a temperature minus a temperature. So it's how much the temperature increased or decreased. Okay, so this is the equation we will be using when we're doing math for specific heat. It's important that we have an idea of this concept conceptually, understanding kind of what specific heat measures, but we also need to be able to calculate with it. Okay, so before we get to doing that, specific heat is the thing I've talked about, and again, it's the variable S in our textbook, and it has the units that we're going to use of joules divided by grams times degrees Celsius. That equation right there, it's the one I just showed you. But sometimes you might encounter heat capacity, which does not have the word specific in it. The heat capacity symbol is capital letter C, and it has the units of joules divided by degrees Celsius. They took the mass out of it. So its equation looks in a lot of ways very similar to the previous one. It just doesn't have the M because they took mass out of it. And instead of S, we just use the symbol C, which stands for heat capacity. So just in case you encounter something with these types of units with no mass, that's your equation. But most often, this is going to be what we'll be using. So let's try an example. So here's a question that involves specific heat, and we're having to calculate it. If I have a 23.1 gram sample of metal that loses 315 joules of heat as it is cooled from 96.2 degrees Celsius to 57.9 degrees Celsius, what is the specific heat? So if we're doing a calculation, and we recognize the term specific heat, you see that. Either they give you the specific heat, or like in this one where they're solving for it, that's your hint that this is our equation. Okay. And then what my suggestion is then let's take all the numbers from the question and one by one assign them which variable letter they go with. And then when we're finished, we'll plug our numbers in. So I'm going to want to figure out what is Q, what is M, what is S, and what is delta T. Okay, so Q is the heat with the unit joules. So when I look at this question, loses 315 joules of heat. So Q is equal to 315 joules. M for mass should be in grams. So I have a 23.1 gram sample. So M is 23.1 grams. S is the specific heat. When I look for that, it says what is the specific heat, so I don't know that. And then delta T is the change in temperature. So I'm going to have to subtract temperatures. 96.2 and 57.9 are the two temperatures. So I'm going to take, as far as you're concerned, you're taking big number minus small number. So when I do that subtraction, I get 38.3. My units are degrees Celsius. So now I have a value for Q, a value for M. I know I do not know S, and I do know delta T. So I'm going to take my equation here, and I'm just going to plug numbers in it. For Q, I'm going to write 315 equals M for mass, 23.1 grams, times S that I do not know, times delta S, or delta T, which is 38.3 degrees Celsius. So my job is to solve for S. Okay, so what I can do is I can take 23.1 and 38.3 and multiply them together. So 315 stays on the left. I'm going to take 23.1 grams times 38.3 degrees Celsius, and I'm not rounding yet, so 884.73 is what I got on my calculator, times S, where again, S is the thing that I don't know. So I need to solve for S. So I'm going to divide both sides by 884.73. And so when I did that, the number that I got, 0.356 over here, I just had the letter S. So units. So that's my number, and I did round it to 3 significant figures, because if you look all of our numbers, 3 sig figs, 3 sig figs, and then what I'm looking at is the final answer there, which is 3 sig figs. But I have to have units as well. So one thing you can do is if you go back to the equation, when I first introduced it, I put the units below them, right? So specific heat S is joules divided by grams times degrees Celsius. So that could be how I know that the specific heat is 0.356 joules divided by grams times degrees Celsius. Or I can know because this number was joules, this number was grams, this number was degrees Celsius, and I took the joules number and I divided it by the grams and I divided it by the degrees Celsius. So if I keep track of my units, I took joules divided by grams times degrees Celsius. That's literally where the units went. Okay, let's try another one where we're solving for a different variable. So, looking at this question, a 20.8 gram object with a specific heat of 2.19 joules per gram times degrees Celsius was heated from 19.4 to 34.1 degrees Celsius. How much heat was gained? So again, my clue, this is the equation I need to use, is when I see the term specific heat being used. That's when you think, oh, it's the Q equals M times C times delta T equation. And then my suggestion is then let's write down our variables and see if we can pick them out from the question. So Q, which stands for heat, and it's in the unit joules. Well, it says how much heat was gained, so I don't know that number. M stands for mass in grams. So we have a 20.8 gram object. C stands for specific heat and has the units joules divided by grams times degrees Celsius. So 2.19 joules divided by grams times degrees Celsius. And delta T is the difference between the temperatures. So I'm going to take the temperatures and I'm going to subtract them. And I get 14.7 degrees Celsius. So now I'm going to take the values that I have and just substitute them in there. I'm going to leave the letter Q as Q because I don't know it. For M, 20.8. For S, oops, sorry, I did write C there. Different textbooks use different letters. So S for specific heat, 2.19 joules divided by grams times degrees Celsius, and then delta T is 14.7 degrees Celsius. So I'm going to, in my calculator, take 20.8 times 2.19 times 14.7. And when I do that, I get 669.6144 units. And I haven't rounded to sig figs yet, but if I look at units, if we look back on the previous slide, or a couple slides ago, it said heat was in joules, so I could know that it's joules. But I can also know it's joules because the grams cancel out and the degrees Celsius cancel out, so the only unit left is joules. So sig figs, well, this number has 3 sig figs, this number has 3 sig figs, and then this number down here has 3 sig figs, so my answer should have 3 sig figs. So 1, 2, 3, but that 9 has to be rounded up. So 670, I'm going to put a decimal place right there, show that that 0 is supposed to be significant, and then the unit is joules. So we didn't do an example where you solved for mass, or an example where we solved for delta T, but between these two calculations, it kind of gets you through the idea that when you're solving for mass or delta T, it's going to be very similar to our previous slide where we were solving for S. So hopefully this helps get you through some of the math and conceptual parts of specific heat.